Let's add a few details of the coupled characteristics. We had talked in some detail about the Kelvin waves in the Pacific Ocean, especially associated with these westerly wind bursts in the West Pacific, which generate Kelvin waves and are part of the El Nino La Nina life cycle. In the Indian Ocean as well, we have Kelvin waves. This is just a plot I took from this, which uses observations and shows coherence of sea level signal across these moorings in the Indian Ocean distributed along the equator, and how much energy actually makes it into the Indonesian seas through the Lombok Strait and the Ombai Strait and so on and so forth. But the main point is that as the monsoons switch from the northeast in the winter to southwest in the summer, in both intermonsoons there are westerlies on the Indian Ocean equatorial region which set off a Kelvin wave and create specific features called the Wordke jet. There is a spring Wordke jet and a fall Wordke jet, which are strong eastward currents associated with downwelling Kelvin waves, which propagate as coastal Kelvin waves into the Bay of Bengal, around and back over around peninsular India, and as Rossby waves out into the Arabian Sea and down here into the coast. And there is interactions between these Kelvin waves, not just associated with Wordke jets, but also associated with the Madden-Julian oscillations that we talked about, and they have specific instabilities being generated here, which then go off as Rossby waves back into the Indian Ocean and affect that southwesterly dome that we talked about. And all these are features in the forced part of the Indian Ocean response, but there are some coupled characteristics like heat balances and potential feedbacks to the atmosphere. As you will see as we go through the chapter, that most of them still remain kind of speculative, in the sense there is evidence that there is interactions between the Indian Ocean and the monsoon. Monsoon forcing of the Indian Ocean response, and potentially Indian Ocean feedback to the monsoon, but there is not very solid evidence other than hints that this is happening. Moisture fluxes are obviously a big part of the monsoon dynamics. The strong southeasterly trades produce lots of evaporation here, and there is some evidence, especially from models and reanalysis, that most of the evaporation and moisture flux comes from here, but there is also strong evaporation over the Arabian Sea, as we have seen by the cold temperatures and the cross-equatorial pressure gradient that's associated with cold temperatures and no inertial instability and so on. But the integrated vertical moisture transport calculated this way that we saw in chapter 1 using humidity distributions and winds produce strong flux over here with some around the Indian Peninsula into the Bay of Bengal. So these things vary on intra-seasonal timescales as well. And of course there are contrasts. The flux over the West African region is not as strong as over here, as we have talked about in terms of the easterly jet and the relations to the meridional circulation over here, etc. So these are obviously monsoonal circulations in terms of their land to ocean feature and the seasonal changes, but they are not as dramatic as the South Asian monsoons. And during DJF you can see that the winds change and the the moisture fluxes are very different, both over Africa as well as over the South Asian monsoon region. So this gives you a sense that strong monsoon and strong Findlater jet or a low-level jet will have certain impact on the cross-equatorial heat transports, as well as air-sea interactions and ocean dynamics themselves. So we'll talk about those after looking at these climatologies of the Indian Ocean region. So December, January, February, you see this nice warm sea surface temperature, which actually doesn't change that much over the year. You can see the 28 and 29 degree isotherms. Obviously March, April, May, when the winds are weak in the intermonsoon. So both intermonsoons, the March, April, May, and September, October, November, have weaker winds. You would expect reduced latent heat fluxes as well as reduced heat transports in the ocean. So the winds again shown here: DJF, northeast monsoon, intermonsoons, southwesterlies, and the intermonsoon, with strong southeasterly trades persisting throughout the year. And there is the OLR. So as we know, the ITCZ is to the south, subsidence and high OLR. MAM OLR is still high, but you can see the changes happening in the ITCZ structure, and then the split that is coming in the summer months that we talked about, with warm sea surface temperatures holding on to the marine ITCZ and the monsoon dynamics over land, and transition back to the winter months through the September, October, November intermonsoon. Okay, so warm SSTs here, and then warmer SSTs during MAM have some consequence for monsoon anomalies. So that's where the quasi-biennial timescale can be thought of, and so on. So you can see warm SSTs here, warm SSTs there, with this cool band in the middle, which is related to that meso monsoon intraseasonal oscillation dynamics that we had talked about, with additional details about how the vertical shear we talked about affects the northward propagation. But there are also ideas that the meridional shear of the zonal winds, seen here, okay, you can see that there is a strong meridional shear here as well, which can produce barotropic instability as opposed to the baroclinic instability in the vertical shear. And there is a debate about whether it's the barotropic instability that provides the energy for the northward propagation or the baroclinic instability, and so on. Okay, so I will leave it here, and we will look at the surface flux tendencies in the next podcast. But you are beginning to get a sense that we are building towards the role of the ocean in the coupled monsoon dynamics. We'll look at further details as we go along.